We have damped electric oscillations. That means we have a resistor present as well. The voltage variation due to this damping is Vm e raised to power minus beta t cos omega t. That is our standard equation of a damped oscillation. We need to find the moments of time when voltage across the capacitor reaches its peak value and reaches its maximum values. So you have to understand what's the difference between these two terms. So we know that the graph of damped oscillations is like this. This yellow line represents the amplitude, and that is the coefficient of cos omega t, that is Vm e raised to power minus beta t. That is what this yellow line represents. So our curve, that is of because of this cos omega t, this whole term that lies between these two curves. Now wherever this red line, that represents the actual displacement, that is the not displacement, the actual value, that is the whole thing. So the red line represents Vm into e raised to power minus beta t into cos omega t. So amplitude into cos omega t, and this is just the amplitude. So at certain points the value of voltage will be equal to its peak value. So wherever that curve intersects, they are those points. So at these points represent the peak values the voltage did reach. However, if you see the maximum values of voltage, so that will be when dV by dt is 0, top of this graph. So at that point it does not reach the peak value. So that's what we have represented here. So this yellow line represents the peak values a voltage can reach, but it cannot always reach. So these are the points where the peak values, the voltage did reach, and these are the maximum values of voltage. So he's asking at what time the voltage reaches the peak values. So at what time this occurs, the intersection occurs, and then at what times the voltage reaches its maximum value. So what time this happens. So I hope it's pretty clear what's the difference between peak value and maximum value. Peak value is represented by this yellow line and maximum value is represented where the curve is flat. So this is our equation. So at maximum values the voltage will be equal to amplitude. So V is equal to Vm e raised to power minus beta t. So that means cos omega t is equal to 1 or plus minus 1, because at bottom also it's happening. So that's why we have taken a modulus. So voltage is reaching its amplitude, which means omega t is equal to n pi. So time will be n pi by omega. Now second point, when it reaches its maximum values, so at maximum values dV by dt is equal to 0. So we'll just differentiate this. So when we differentiate this, we get this equation and then we equate it to 0. From here we get tan omega t is equal to minus beta by omega, or omega t is equal to n pi plus tan inverse minus beta by omega. So you can see the time where the peak reaches is slightly less than n pi. So that's what it represents. So this will be the values of n pi. For example, right here you can see when n is equal to 0, this point is reached, and this yellow line will be on pi when omega t is equal to pi, and the red dots will be slightly before them, that is n pi plus tan inverse minus beta by omega. All right.